A machine learning agent triggers a catastrophic failure using a piece of data it retrieved with 100% accuracy. The system executes a disaster not because the search failed, but because the retrieval was flawless. Standard industry practice treats agent memory as a search problem. Engineering efforts focus on optimizing vector databases and retrieval-augmented generation to ensure an agent can pull precise text from its past. Consider an agent that retrieves a cached API key to execute a tool call, unaware that the user revoked that key's permission 2 days ago. The search is successful. The resulting action is a security breach. In their 2026 paper, Ding and colleagues argue that as agents accumulate state across sessions, the primary risk shifts. The danger is missing governance. Proving that an agent uses retrieved evidence accurately is insufficient if the system cannot verify the evidence was authorized for that specific task in the first place. We must distinguish an episodic agent from an always-on agent. The behavior of an always-on system relies on durable state accumulated across earlier interactions. This persistent state extends to task ledgers, external commitments like calendar entries, and explicit user permissions. Governing this state requires a mathematical model of a persistent record. The researchers represent every item of state with this model. The variable v represents the value, or the text content itself. In most production systems, this is the only variable currently stored. The remaining 7 variables, authority, scope, mutability, provenance, recoverability, actionability, and timestamp, comprise the governance envelope. Treating agent state as text content to be stored and retrieved ignores that entire envelope. This creates a structural blind spot that compromises system safety. These 7 envelope variables function as strict engineering requirements. Look at this database record. The text value is visible, but the 7 governance columns are empty. If we attempt to identify who authorized this fact by reading the text alone, the query fails. This extraction fails because governance metadata cannot be derived retroactively from the text. The source, scope, and expiration of a preference are not encoded within the preference itself. This gap widens during standard machine learning consolidation. When systems use an LLM to summarize past interactions, they compress the text but drop the surrounding envelope. The resulting summary allows the agent to make the same decisions as the original data, but carries none of the original permissions or scope limitations. Discarding this envelope severs the connection to the record's authority, leaving the system with no mechanism to control that state. Sophisticated data compression that fails to preserve these 7 variables trades system control for a minor gain in storage efficiency. Within the envelope, the actionability variable determines the real-world stakes of a system failure. If an agent retrieves a poisoned reflective lesson, like poor advice on email formatting, the error is contained. The output degrades, but the harm is minimal. High-stakes operational failures are different. If an agent retrieves a poisoned procedural skill and executes it in the real world, the failure has physical consequences. Treating all memory as an undifferentiated RAG substrate ignores the fact that different types of stored state carry vastly different risks. A typed record moves through an agent's architecture in a 9-stage pipeline, divided into the forward arc and the return arc. The forward arc governs the accumulation and use of data: observe, write, validate, organize, retrieve, and act. Here, most engineering effort currently resides. The return arc, update, forget, audit, and rollback, is responsible for governing and recovering that data. In many current systems, this half of the loop is missing. Considered a requirement of deletion propagation, a user's request to forget a record must mathematically scrub that data from all downstream derived summaries and embeddings. There is also the need for rollback traceability. Every executed action must carry a digital handle pointing back to the specific records that justified it. Both of these safety requirements live exclusively on the unbuilt return arc. Without a rollback stage, recoverability handles stamped during the act phase are useless. The system records the handle, but has no mechanism to use it. Agents are built only to act forward, leaving them without the architecture required to govern backward. The Always-On Evaluation Protocol, or AOEP v0, establishes a deterministic ADA contract to measure this governance gap. The protocol excludes LLMs as judges. Because language model biases can mask systemic governance failures, every check in this protocol is fully deterministic. The evaluation uses a split scorecard: left, obligations; right, negative invariance. A system with 0 memory scores 0 out of 15 on obligations, but a perfect 41 out of 41 on negative invariance, simply because it has no data to leak. A single averaged score would reward this total amnesia. Instead, recall capability and state governance must be evaluated as separate, adversarial metrics. Empirical pilot data tested standard memory substrates against these positive obligations. Raw storage and RAG systems score 7 out of 15, passing semantic recall but failing governance. Sophisticated extraction tools like mem0 score 3 out of 15, performing worse than basic raw storage. This failure stems from the extraction process itself. Fragmenting events into atomic facts often destroys the causal links the governance envelope needs to function. Engineers should not confuse a storage substrate with a governance architecture. A vector store that retrieves an expired permission is performing its search task while failing its security requirement. If an agent's future behavior depends on its past, safety is not a retrieval problem. It is a problem of building the return arc.